My name is Matthew Johnson, and I would like to tell you about a method that our group has come up with in order to implement mineral dust as a climate solution, as a geoengineering solution. And we've named this the KHEPRI Project. And this is a small study, kind of a pre-study that's part of a larger project in order to control the atmospheric methane concentration. And just to begin by talking a little bit about methane. So these are 4 quick facts about methane. The first one is that it's a very important greenhouse gas. And if you look at carbon dioxide, everybody is talking about carbon dioxide, but methane has almost as large of an effect on climate as carbon dioxide does. So it doesn't receive the attention that it deserves as a greenhouse gas. The second thing to see is that its atmospheric concentration is increasing very rapidly. And this is the instrument record going from the early 1980s up to the present day. If you go back to the pre-industrial concentration, methane has more than doubled during that time. So it's increasing rapidly, and it's an important greenhouse gas. The third quick fact is that it has a relatively short atmospheric lifetime, and it is shorter than the other long-lived greenhouse gases. Carbon dioxide stays in the climate system for many centuries. The CFC gases can be 100 years. There's something like carbon tetrachloride that could be 50,000 years, and laughing gas is over 100 years. In contrast, if you can do something about methane, you can see the effect rapidly, right? So we're looking at a decade lifetime if when you could really do something, for example, to save the polar ice cap and have an effect here and now. The next thing that really makes sense in economic terms is that you have a very large global warming potential for methane. And that means that removing a pound of methane from the atmosphere has the same effect as removing 84 pounds of carbon dioxide, right? So on a mass-to-mass basis, you amplify your effect by that factor, the global warming potential. So we think that methane does not punch its weight as far as what people are talking about. There's a lot of talk about controlling carbon dioxide, rightly so, but we believe that methane really would give you a lot of bang for the buck and produce results now that would have an effect on climate. Very quickly, to talk about the process that we would like to use. And it's important to point out that this is in analogy to naturally occurring processes. And so there's a lot of mineral dust that's coming out into the atmosphere. For example, in the United States, about a month ago, there was a huge cloud of dust from the Sahara. They said that it was the largest such cloud in the last 50 years. And these minerals, it contains a lot of titania, a lot of iron oxide. This is simply rust. And these act as what we call photocatalysts. That means that they convert sunlight into chemical reactivity. And we can use them to change chloride into chlorine atoms. And the nice thing about chlorine atoms is that they react with methane and break it down into carbon dioxide. We would have that chlorine present either because we add it into the source material or because it's naturally present in the atmosphere. It's part of sea spray aerosol, and we've all seen the sea spray in the atmosphere that has a lot of chloride in it to begin with. We also feel like we're on very safe ground as regards toxicity, since we're using materials that are found in the environment to begin with anyway. We're enhancing the concentrations, but we're using processes that are already occurring in the Earth's atmosphere. So we convert the methane into carbon dioxide. A lot of the carbon dioxide is going to dissolve in the ocean. All right, if we get into the details, we see this one small project as part of a larger series of events, and the final result of this is a working climate remediation method. We have the concept already of what we need to do. Right now, we need to generate some fundamental information that will then be the input of models that we're going to run in order to find out the impact on the climate system. Once we find out how we would locate this climate remediation system, we then go into the design phase. We have some sort of a tower that would deliver a plume of this dust into the atmosphere. We would install it, and then we would start removing methane from the atmosphere. So we know that the reaction happens, but we need to learn some of the details of what is the effect of temperature, what is the effect of relative humidity, and what is the effect of the particle size on the efficiency of this process. And it might be that we would choose to locate the installations in the tropics, because then there's a lot of sunlight, and the transport of the atmosphere is going to be bringing these into the entire atmosphere. Then we have certain conditions of temperature and humidity. We might choose, I don't know, to locate them near the Arctic areas where you have permafrost that's melting and it's a large source of methane. But that would be entirely different conditions in terms of temperature and humidity. So we just need to do a model in order to figure that out. What is the best way to deliver this? This next slide is showing a bit of our work plan. And my students in Copenhagen have already started to do some of the initial studies. They've set up this system, and as a proof of concept, we show that we can start out with this salt solution in the liquid. We put it through an atomizer, we modify the air a little bit, and we end up with these particles inside of the reactor where we can do some tests. And rather surprisingly to us, we were able to achieve an extremely small particle size very soon after we first turned this on. So we're making particles with a size of about 40 nanometers, which is about as small as you could ever wish to achieve. These are so small that they're almost completely surface, and it's the surface that gives us the reactivity. So having very small particles will increase the impact that we get out of a certain amount of iron that we're adding into the material. We're also able to control the humidity and the temperature inside the reactor. So we're pretty much ready to go. We just need the resources in order to do the experiments and do the data analysis. I definitely do think that we can remove methane from the global atmosphere and help cool the planet. I've put together a small budget for this project. I'm sorry, but we are denominated in Danish crowns, but you can easily transform these amounts into dollars, and then it comes out into a total sum of $50,000. The main component of this is to have a researcher who can be in the laboratory and conduct these studies. We also have a small budget for consumables. And very importantly, we have David Miller as the consultant on this project, who's working with communications and with bringing this out into the world.
Thank you for watching this presentation by Matthew Johnson. Please visit our website to learn more and check out our social media pages to stay updated on how we remove methane and restore our climate.